Ladies and gentlemen, hello and welcome, coming to you once again, not quite live, from One Take Studios, where we are walking into an aura of mystery and intrigue today. Ladies and gentlemen, Additive Ciphers. Specifically, we are currently working with cryptological mathematics, so putting things into secret code, taking things out of secret code. Specifically here, we're not working with anything that's too crazy. Oops, peeking up. Nothing super crazy here. We're talking about monoalphabetic substitution ciphers. If you analyze that, it is what it sounds like. Monoalphabetic means one member of the alphabet, and substitution, we're subbing things out. So we're going to replace one letter of the alphabet with another letter of the alphabet, and today's topic is going to be how to do that with addition. So, here's the concept. We are going to have a plain text character replaced by another character that's a certain number of units away. Plain text is something that is not in secret code. So we start off with something not in secret code, and we're going to essentially bump it down the alphabet, move a certain number of places away to create something new to take its place. So the number of units away the new letter is from the old letter is going to be called the key. And if we want to say that the key is 3, here's what that would look like, at least to start your alphabet off. So A, B, C, D. Notice the lowercase letters here. Oftentimes we are using lowercase to suggest plain text. In other words, these letters right now are not in secret code. They're just plain. Well, these are the 1, 2, 3, 4, and 5th letters of the alphabet. And so knowing the number that's associated with each member of the alphabet is actually helpful. If you don't have an entire alphabet list numbered, you might want to do that. Stick that in your margins of your notes someplace. If my key is 3, and if I'm using an additive cipher, the idea that is I want to take each of those numbers and I want to add 3. Doesn't seem like that's super crazy. Adding 3, 2 plus 3, 5 plus 3, there we go, to create these new numbers. What does that mean? Well, that means that the letter A in plain text is going to be replaced with the 4th letter of the alphabet, which is actually D in ciphertext. And so the uppercase letters then we are using to represent things that are in code. So out of code, the letter A is going to be replaced with the capital letter D in secret code when I'm putting a word in code. B becomes E, C becomes F, and so on and so forth. Not a tragedy. Slightly interesting, however, would be what happens at the end of the alphabet. If you think about it, you can probably figure this out, but we're going to look at it. What happens if I continue my example here and I've got X, Y, and Z? Well, those are the 24th, 25th, and 26th letters of the alphabet. If I continue my key of 3, I can add 3 to each of those numbers, which means 27, 28, 29. For those of you playing along at home, you might have realized that the alphabet only has 26 letters. So what am I going to do with 27, 28, 29? How is that going to work? Well, the concept is this. I'm looking at wrapping this back around. The concept of modular arithmetic. That after 26, I'm going to look at remainders wrapping back around to 1. So 27 is 1 past 26, so we're going to call it a 1. 28 is 2 past 26, we'll call it a 2. 29 is 3 past 26, and what that actually means then is that the X, which is the 24th letter, is going to be replaced by the first letter in the alphabet, which is A. So X, Y, and Z become A, B, and C. So when we reach the end of our 26 letters, we're going to wrap around and grab the first 3, because our key is 3, and use that to end the alphabet. All right. So what does that mean about deciphering, taking things out of code? Well, if the key was 3, and I'm using 3 to put things into code, the inverse of that is what we're going to use to take it out of code. But keep in mind that this is an additive cipher still. So despite the fact that some of you are saying, well, what if I just take like my G, and that's the 7th letter, and I'll subtract 3, and that'll be 4, and that's the letter D. Could you do that? Yes, you could. But if you're doing things that are a little bit more complex, chances are it's not just you and the alphabet hanging out. Chances are this is something that's a larger part of a computer program, and things can be a little bit dicey from time to time. So what we're going to say is there are 26 letters in the alphabet. -3 is the additive inverse of +3. So what happens if we combine our 26 letters with -3? We get 23. In other words, to decipher everything, they are suggesting that 23 be the deciphering key. 23 is the magic number to take it all apart again. Can I make some sense out of that? Well, probably. If you think about two alphabets lined up, what we did originally is took one alphabet and slid it down 3 units, and then realigned the letters and called it good. Well, if we already slid it 3, if we slide it 23 more, that means we will have slid it 26 spots and everything is back to where it started to begin with. There we go. Alright, so let's look at this in action. I just chose a 4-letter word, but something that's got the end of the alphabet. No, not that kind of 4-letter word. Come on now. Here we go. Yes, there we go. So the word is stay. Notice the lowercase, so we are in plain text right now, and I'd like to put this into secret code. I'm going to stick with my key of 3 right now, just because, why not? And I'm looking at, originally, S is the 19th letter, which means T is the 20th letter of the alphabet, A is the 1st letter, and Y is the 25th letter of the alphabet. If I'm using an additive cipher with a key of 3, that means for each of these I'm going to be adding 3, adding 3, adding 3, adding 3. So 19, 20, 21, 22. 22 is my new number, my new place in the alphabet here, and this will be 23. 1 plus 3 is 4, and 25 plus 3 is 28. Alright, so what happens there? Well, now my 22nd letter of the alphabet is what? Do you happen to know that one? I don't. I'm looking it up right now. That's going to be V. So V, capital V, is my ciphertext, and V will be used to represent the letter S when I put this into code. T, 23, well, what's after V? Last I checked, yep, double checking just to make sure, it's going to be W. And then the 4th letter is A, B, C, D, so D is going to replace A. And then Y, well, okay, again, so this is 28, right? How far past 26 are we? 2 units past 26, so this is kind of like using a 2. You would say that we're doing this mod 26. In other words, after 26, modular, we're going to wrap back around again. This is actually 2 places past, so that's going to be a capital B. So, when I put the word stay in as a secret code, it's going to look like, there we go, there we go, V, W, D, B. All capital letters, again, to indicate that we are in ciphertext. This is my secret message. So, if you intercepted the message, VWDB, is the first thing you would say is, hey, I think that's the word stay. Probably not so much, and that's why we're doing this. Is this really difficult to take apart? No, but we gotta start someplace, so let's make it interesting, shall we? Let us go in the reverse. So now I've got, for the second half of this, here's my VWDB. How do I take this back apart again? Well, what we are saying is that if we use 23, we can make this work. So we added 3 to get everything into code. Using the inverse, we will add 23 to get it out of code. Adding 23, adding 23, and you're like, this is ridiculous, why don't we just subtract 3? Well, we could. We could subtract 3 here, we could subtract 3 here, we could subtract 3 here. The problem would come in subtracting 3 from 2. Because 2 minus 3 is -1. And -1 is not associated with a specific letter of the alphabet. While you and I might be able to figure out what letter that should be, if I'm running any sort of computer program, the -1's not going to register. But the 23, this is actually going to work. So if we add these things up, this is going to be 45 and 46 and 27, because I can do this, and 25. Well, again, so after we run all these, mod 26, in other words, after 26 it wraps back around again. Well, wraps back around again how many times? 45 is actually, do I want to switch colors? Yeah, I do, just to be on the safe side. 45 is actually 19, that's in purple in case you can't tell, 19 numbers past 26, and hence that's where we're getting S, lowercase, to take it out of ciphertext back into plain text again. So by taking V, which is the 22nd letter, it was in secret code using the number 3. We're going to take it out of secret code using the number 23. 45 is 19 numbers past 26, and that 19th letter of the alphabet is S. So same thing here. 46, how far is that past? Well, that's 20 numbers past 26. There's my T, lowercase. 27 is only 1 number past 26. The first letter of the alphabet is A. And then 25 is actually within 26. I don't need to worry about that. So the 25th letter is simply Y. And I can take it back out of code. All right, so that is kind of what we are looking at here, folks. Putting it into code through addition and taking it out through addition if possible. If you want to do it through subtraction, I'm not going to stop you, but understand that if you're using this on any sort of larger scale, it's going to make life a little bit more interesting. The biggest problem with this, honest to goodness, the biggest problem is usually not understanding it, but it's putting it into practice without making a mistake. To get all the numbers perfectly right, to get all the letters perfectly right, and not make a mistake, it takes a ton of focus. So that's going to be your bigger deal more than anything else is, can you make this happen? Can you create something in code that people can actually take back apart again? I don't know. I guess we'll find out. All right. Have fun.